Okay, let's see how this goes today. All right, hello everyone. Let's fire into this here. Close. Sorry, I was trying to get all my windows open here. What I want to do really quickly is Blackboard is immensely slow at getting things up. I have to load everything individually. I can't do it in bulk. So I'm trying to get what are they called? PowerPoints up to you guys. As we have finished chapter 8, you have an exam coming through, and I'm talking about chapter 9 in the printed book, which on the online version of the book is chapter 12. And so I think I'm going to start everything with chapter 12, what we're doing and working our way backwards from it. So Stacy has a question about the Pearson going, is it a test? Is it a real test? Yes, it is. I have, that's why let me plop into Pearson here and see if I can show you this. Let me, get to the browser here. I'm not flipping over to the browser just yet. Make sure I'm not showing any sensitive info, but there we go. All right, so go into the assignments here, and this is a list of the assignments. I just put up a homework due on the 19th. The word problem exam is an actual exam. The practice exam is set up identical to the real one. And so the practice one is to get you used to Pearson. I would do the practice. Don't worry about it too much. Just figure out what weird stuff Pearson's doing. Figure out how you need to write things down and do them out and then put them back in. The actual exam is this word problem exam. And if I look at the settings for it, is this the actual exam? Yep. Yep, you have 3 attempts on it. And you have a save later option. You can leave and return to complete the test. I cannot change this, not access the questions they answered in earlier sessions. So the idea is once you start taking it, try to take it into one go. But if you're having computer issues or something, I understand. And so I wanted to put the save option in there. Gave 3 attempts on the exam because this is new. I don't want the format to be the thing that ticks you off. I want to see your knowledge on it. So that's how I have set that up. That page, let me get out of my browser here. Back over to the wonderful Blackboard drawing that I have. And I'm sorry, I'll try to speak up. I added 2 microphones now. Here, I'll show you just for, that's not me. It's me and my headphones. Let me see if I can get this working here. So I've got my one microphone over here, and then I've got this, whoops, dirty laundry. Oh, not show the dirty laundry. This microphone here. And so when I'm sitting here, this is my eye view. When I go to work on the tablet, this one picks me up. When I go to work on the computer, that one picks me up. But in doing so, I'm really loud in the headphone thingies. And so being really loud in the headphone things, I've started to whisper again. So I think what I might do is I might just get myself out of my own mix here, and then I can just talk normally. And then at that point, I guess I don't really need the headphone thingies on anymore. But it feels better to have the headphone thingies on. Not that you guys need to know any of that. All right. So Stacy, does the practice one help your grade at all? Yes, it does. I'm treating that like the worksheets, and so it's graded like the worksheet. Because I can't do any of the in-class worksheets, I've put them onto the practice exams, but I'm doing it in the format of the exam to get used to it. So, and yes, Janine Pearson is lame. That's why I only use it for the homework. In normal situations. We are not in a normal situation, so I'm using the things to the best I can. And if we have any major problems, we'll talk and work it out. Right? We will find ways to do what we need to do, and for me to test what you need to do. Thanks, Stacy. That's a much happier than the other face above it. All right. So I'm talking about equations, and this is always hard for me, and I'm looking at redoing the order. I do things in the book for this because I talk about it early on. And then I come back to it and expand it. But I guess in general, that's how we've always kind of done the algebra thing, is we learn it in bits and pieces, and then we let it grow as it comes through. And I am really, really big on the idea that whatever you do to one side of the equation, you can do to the other. Solves everything for you. And so once you're in that mentality, you're good to go. So let me get through here. I'm trying to get to where we were. And so we started to look at the idea of a linear equation. So let me put this up here. I'm going to use these slides and go back and forth to the Blackboard type thing over the slide usage. I just need to make sure that I can see your stuff. I have two monitors, but the second one isn't working with the laptop right now. And I've been focused on the material more than getting that up. So I'm kind of like wedging things onto a screen to see things here. So when you hear the tap in the back, that's me frantically moving stuff with my mouse. So you should see right now the idea of the linear equation, where if we look at it here, we have a variable and two constants. And the thing about the variable is there's no power to it. There's no exponent to the variable. Towards the end of this, we'll see that we can add exponents to it. And we're going to find a way to graphically represent these things. And so calling it linear has a graphical representation. And we're going to see that letter A hanging out in front of X is very important. What we multiply things by X by is very important. For right now, this one variable equation we can solve. And so in solving, what we tend to want to do, if I'm going to take this form here, I'm going to write it on my Blackboard thing and show what we end up doing for almost all the problems we do. And I'll do it in this really generic format. So I have ax plus b equals c. And so I have something times x plus another number equals c. Now this can be a negative or positive number. This can be a negative or positive number. This can be a fraction, so it's really a division. Right? All of our PEMDAS stuff. Right? I can say I'm multiplying a times b. I can say I'm dividing a divided by b, or I can turn that into a multiplication of a times 1 over b. And so, and addition is a plus b, subtraction is a minus b, which we can turn into an a plus negative b. And so you know me, I overly emphasize this. These are really the same thing. So this is saying I have a division or multiplication, I have addition and subtractions. Now I can string together, I can have I'm going to give it little numbers, x plus a 2x plus b1 plus b2 equals c1 plus c2. I can have loads of different terms. But I hope you can appreciate if this was 3x and this was minus 2x, they would come together to give me 1x. And so once I gathered up all the like terms, which is something we looked at the end of the last chapter, like terms, when you have the same variables, you can add up all the coefficients. Once I have all the like terms together, this is the simplest this equation will look. I will have something of x plus or minus some number equals some number. Now there's some tricks in there that we want to get to, but this ends up being our goal. However ugly and chaotic it looks, we try to make it look in this form. Because in this form, I'll change my colors and move over to the side here. This is worse than having like tons of colored chalk. It really is. I could pick any color I want on my color palette. All right. Oh, and I did get a blackboard in my house. I now need a camera to replace the webcam because this can't focus on text. So I might have my chalk again. So I think that's just to keep me from going more insane. So I'm going to rewrite this in this form here. And so our idea is to get x on its own. So I would subtract b from both sides. And then divide by both sides by a. And that leaves me with this. And so getting in this form, we will always have a method of get the numbers to one side, get the variables to the other. Get the numbers to one side, get the variables to the other. But visually, this is going to tell us some information about things. And so as we do this, whatever you do to one side, do to the other, we need to remember that it's working its way towards solving for x. But this intermediate point, all of the one variable in one place and on one side of the equation, plus or minus some number equals some number, right? All of the variable on one side of the equation, plus or minus some number equals some number. And from there, this steps, plural, will be fairly consistent. You get the numbers on one side, divide by whatever's in front of x. And so I think that's why the book emphasizes this particular form. What's really, really nice is we're going to learn a trick that the French gave us in the 1600s, and that trick's going to let us do this in two variables. It's not, two variables isn't that bad. But that'll let us use graphs. And so we can take all the information that we get from being able to get up and walk to the door, we'll be able to use to describe our numbers, right? Because we deal with geometry every day. We have words for it. We go up, we go down, we move left, we move right. And this trick the French did, we can start describing our equations with that because they made graphs out of them. So that we don't have to learn any new words. We can just look at it and go, hey, that thing's getting bigger. And we plug in the numbers and hey, the numbers are getting bigger. And that's why the word linear is really important here. That's why I'm ranting on about it for a while. All right, so let me get back into this here. And so we also have something called equivalent equations. So we're getting some definitions here. And so we have equations that end up having the same solutions. They might look different to start with, but once you get all the variables together, they end up being equal. And this is kind of all the stuff we talked about last time as we worked our way through it. And then we solved some examples of solving some equations where whatever you do to one side, you do to the other. What I want to do is look at how this works in word problems, because the whole value of putting things into equations is getting the ability to take reality and put it into our algebra system. So what I'm going to do is I'm going to scroll down here and we're going to look at this problem in the book. All right. And it says the mean distance, or the average distance. Well, let me read it first and then I'll break it down. The mean distance between the planet Venus and the Sun is 31.2 million miles, more than than the mean distance between the planet Mercury and the Sun. Use the diagram to write an equation to find Mercury's mean distance from the Sun. Solve this equation. So here we're going to go. Let's get to this diagram and we'll see. We'll go here. So the distance from Venus to the Sun is 67.2 million miles. All right. Its mean distance. Let's go back here though. Whoops, sorry. We'll go back here though. So this distance between the Sun and Venus is 67.2 million miles. If we go back, whoops, backwards, not forwards, the mean distance between the planet Venus and the Sun is 31.2 million more than the mean distance between Mercury and the Sun. So between these two pieces of information, we know two things. We know how far Venus is from the Sun, right, 67.2 million, and we know how much further Venus is than Mercury, but we don't know Mercury's. And so what we'll do here, I'll come back to the blackboard, and I'll say, hey, M is the distance from the Sun to Mercury. And I do apologize for switching back and forth between these slides. Remember, if we were in that crazy little classroom, part of the stuff would be on one board and one would be on the middle board. If I split it on the screen, the text gets so small none of us can see it. And so we see Venus is 31.2 million miles more than Mercury. So I'm going to switch back to the blackboard here. So Mercury plus 31.7, and I'm not going to write the million, right, is equal to, and I'm actually going to put another variable in right now because I have to switch through slides and I don't remember that number. So I'm just going to say the distance to Venus. Venus, and look, we can read this now like a sentence. Venus is 31.7 million miles more than Mercury. See how our symbols translate back into the sentences here? Right? Venus is 31 million more than Mercury. All right. So that was our first piece of information. Our second piece of information was the total distance to Venus, which is 67.2 million miles. So, and I will do this in a little mathematical trickery, or let my symbols do the work for me. Whenever I say mathematical trickery, it's usually the symbols are doing the work for me, right? So the distance to Venus is 67.2 million miles, 67.2 million. Oh, and I did, look at this. Look at my typo dropping between slides here. 31.2 million, right? But I did 31.7. And it looks like everything has a 0.2 on it. My apologies. I'll get an eraser here and we'll fix this one. Let's see. Let's get a good eraser. Oops. Erase. Isn't that pretty looking? Weird in the animations. All right. Here, 31.2. Luckily, when you're doing this problem, you can have your paper off to the side and have everything up in one place. Again, I'll get my second monitor together. I'll make less of these. But here's the mathematical trick that I want to show. Whenever I have an equal sign and it says V is equal to this, I can take whatever I see on this other side here, and wherever I see V, substitute it in. This lets me plop in no matter what I have on the left-hand side. It doesn't have to be just one letter. It could be a whole expression. If I see that whole expression somewhere else, I can drop it in. Sorry, answering the question. All right, so let's get back over here. So the ability for me to substitute all of this in like for like, I'll come in here and I'll just drop that in. So mercury plus 31.2 is equal to 67.2. This is really the key to algebra as being a tool for the real world, is things that we don't know what the values are, get placeholders. And then when we find out particular parts of them, we have a relationship between things, right? The relationship between the distance to Venus and the distance to Mercury. There's Venus is further away from the sun than Mercury is. So there is an additional distance that says, hey, I'm further away by this much. And that's our relationship. And so let me drop back to the slide part here. They tell me I didn't drop on the slide here. I hate when I do that. Let's go back to 2 steps here. There's the blackboard. There's the slides. There's the blackboards. There's the slides. All right. Blackboard, slides. All right. And so this relationship, Venus is 31 more than the distance to Mercury, is the first relationship that we describe. And there's our first relationship we describe. Venus is 31.2. Venus is 31.2 more than Mercury. When I come to my next relationship, I have the distance Venus is from the sun. So I represent that relationship with Venus is the distance it is away from the sun. Wherever I see this definition, V equals, or whatever jumble of mess I have here, I can drop in to where I see the exact same thing. And I can take all of this now and I can isolate it to find the distance for Mercury. And this is where my mantra comes in. Whatever I do to one side, I do to the other. What I want to first note is this is linear. This meets our definition for linear. I have a variable plus some number equals some number. And that variable is multiplied by our hidden 1, right? We don't worry about those ones out front because anything times 1 is itself. And so my job is to isolate the variable all on its lonesome. In the way of the variable is this 31.2, and it's positive. So I want to reverse that addition by subtracting 31.2. But whatever I do to one side, I do to the other. And so my distance to Mercury, 0.2 minus 0.2 is 0.0, 7 minus 1 is 6, is 36 million miles. And so Mercury is 36, and I will add the million there, million miles from the sun. And so this is why we work on solving these equations, why we work on trying to get these relationships together, is not that the math tells us about reality, but reality tells us about a pattern, and these variables let us hold the thing we don't know at the moment and let the pattern help us put put everything together. Great, now I'm going to start cracking up on the microphone, trying to figure out what a virtual disruption is like. See, I'm the teacher. I can't comment on the screen name. All right, so let's see here. I'm going to clean off the board here. And so a lot of our focus on solving equations will be, there's the textbook part of it, right? And in a textbook part, I go, hey, I have 3x plus 9 minus 4x equals 2x plus 1. And when we write an equation for an answer, do we plug in the numbers given? It depends on what numbers are given, right? In most cases, yes. So that v equals 61.2 or 67.2, sorry, is definitely that one goes in there for v, wherever we see v, and it will replace the placeholder we had in v. Sometimes we don't have a number given for a variable, but the relationship solves it. And that's kind of where I'm looking here. Without doing this from a word problem perspective, we have a relationship. And this relationship stresses many things in variables. So we spend time practicing isolating the variable so we can figure out what it is. So there are two ways variables get used. One is they're placeholders in things like formula, and once we have the measure, we plug them in and get answers. The other is they're a placeholder for a pattern, and when we see the pattern out like this, we solve. And so solving is a unique term. So if I say solve, what I mean in a textbook problem here is I isolate x and I find out what x is. When I have a formula or another relationship solve, could be plugging in the numbers for all the variables, or it could be isolating the unknown thing. We have to look at the pattern that comes out from it. So for example, I'm going to continue this here to show the idea. So what I'm going to do here is I'm going to solve this ugly thing I made just to show that we have a pattern. And I'm going to start with just working the left-hand side. I'll then bring the sides together. And so I have a term of an x and an x here. So 3x minus 4x is negative x, and I have a positive 9. So I've gathered the like terms on the left-hand side. Now I want to get all of my variables onto one side. It doesn't matter which side I get them on. We have a tendency to say, hey, put the variable on the left-hand side because that's how we were taught to read them. I have a tendency to keep things positive. And so this is a negative x. If I were to subtract this from both sides to get it over here, everything would be negative and I'd have to divide by a negative. But if I add x to this side, well, whatever I do to one side, I have to add to the other. That would cancel here, leaving me with 9. And 2x plus x is 3x. And I still have the plus 1. So now my job is to get rid. And notice I have gotten this into its linear form. And that's the emphasis I wanted to do with the linear form. I have some number times x plus a number equals a number. I just have it backwards, right? We saw this as 3x plus 1 equals 9. Nice thing about equal signs, they're the same either way, so I can write them in any order. So maybe I'll switch it like this. So notice what I'm doing here. I'm going to stop, I'm going to rewind, I'm going to go back a bit, and I'll keep going back and forth with this. I gather like terms on one side. This side didn't have any like terms to gather, so it came down on its own. So, and the like terms here were the x. I had 3x minus 4x. That gave me a negative x. And I still had the 9, so I gathered like terms. Now I want to get it where all the variables are on one side. I want to get it into my linear form. So I added x to this side to get rid of it. That left me with 9. Whatever you do to one side, you do to the other. So I added the x here, and that gave me 3x plus 1. Now I'm rewriting the sides of the equation. I'm happy with the 9 equals 3x plus 1. I'm really going to emphasize, though, it's an equal sign. I can switch the signs around whenever it's visually good for me, as long as I take everything, right? All of this has to come over to the left. Now this is the linear form. So my idea is to isolate x. So I'm going to subtract 1 from each side. And then I'm going to divide each side by 3. And so x equals 8/3. And if we want to write it in the mixed form, it's 2 and 2/3. Hello, Ben. Wait. Okay. All right. This is like Bart calling the Moe's. All right. I'm just going to ignore it. You put those two names together and it's scary. I'm going to focus on algebra. I hope you appreciate it in this last step that this is what we're trying to do, is to get things into the linear form, because once we're in the linear form, we have the ability to simplify. And that linear form is some number times a variable plus a constant equals a constant. All right, I'm going to look at I'm going to look at the multiplication and how multiplications come up in word problems. So we've got this, we do anything to one side, we do it to the other. And what I'm going to do is we're going to look at another application of this and apply that coming off. So let's go here. And so again, we're focusing on these equations. We're going to learn to get these equations from reality. But now we're using equations, not just the textbook problems. Okay. All right, so not having a Jacob Miller in the class and getting that disruption there, I just had to remove that person. Sorry about that. Okay. So let's look at this particular problem. So a student applies for a job that pays an hourly overtime wage of $15.90. The overtime wage is 1.5 times the regular hourly wage. What is the regular hourly wage? So this is the part we all hate, is putting all the words together and getting equations out. So what I like to do is kind of focus on each sentence and look for the keywords. So a student applies for a job that pays an hourly overtime wage of $15.90. So $15.90 is going to get multiplied by any number, any hour. So come over to the blackboard here. I have some rate of 1590 that I'm going to multiply the hours I work by. And the overtime wage is 1.5 times the regular hourly wage. So overtime is 1.5 times whatever this regular rate is, 15.90. So we're looking for what is the overtime rate. And what I want to do here is I want to jump to how we can put this all together. So this would be how I would use my wage to calculate my salary. All right. I would do 1590 times my regular hours. And then I would do my overtime rate, which is 1.5 times 1590. Sorry, my handwriting is going a little bit there. $15.90. Yeah, I keep getting on that. $15.90 times whatever the overtime hours are. So let me just call those Y. And that would give me my wage. But for right now, we have this part here that we're not sure of. And so what we want to do is we want to solve for all right. Can you guys give me a second here? I've got people jumping into the channel here that aren't in the class, and they're flooding out my feed here. So give me a second. I'm going to come back to this problem. Just hold on for 1 minute. I'm also going to swear, so if you have the swear jar thing going on, add a couple to it. All right, I think you can put like $3 into the swear jar there. I muted it and swore a lot, but it's okay. I'm gonna restart this problem. I was definitely distracted for what I wanted to do on it here, so my apologies on that. Yeah, Stacy, how do random people stumble on it? I don't know. I've been getting comments on the videos for a while. I think they just, search and see what I'm doing. The thing is, like, I am not. I like what I'm doing for you guys. This is definitely not what I would post on my YouTube feed normally. Um, so, are you having audio? No, I turned off the audio. You should be getting audio now. You should be getting audio now. All right. I'm going to erase the board. You do like this blackboard a lot better. Oh, that's good. Yeah, I'm not a big fan of the Zoom tech. It has some security flaws. I'm actually a big fan of having no security at all, where people can come in like this and you expect standards of people. Um, in general, though, I've never had an issue with it. Again, I think there's a large chunk of the population um, just sitting there chilling and bored. And unfortunately, I think the modern mentality of boredom is to, hey, let's mess with people. So that's okay. I shouldn't have let myself get distracted there. I'm cleaning off the board here, and I'm going to reapproach the problem after that. So let's see here. I definitely miscopied something down there. Boom, 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 boom. All right, let's go back to this slide. All right, so as Janine so rightly pointed out, that I miscopied this down. So a student applies for a job at oh, dog. I mean, I liked them too. It was just the questions, and I knew the questions were going to flood out since he started asking trig type things. So it was he. I'm assuming it's a he. They started asking trig type things. And so I just wanted to silence it so that the questions wouldn't get too large. All right, so a student applies for a job that pays an hourly overtime wage of $15.90. The overtime wage is 1.5 times the regular wage. What is the regular wage? So we don't know the regular age. And so what I really want to do here is I want to talk about the thing I don't know. Right? That's what we want to do with our variable, the unknown thing. And so I will again go back to R is my regular wage, and my overtime is 1.5 R. And I know that my overtime wage is $15.90. This goes a little bit quicker when you can think clearly. And so I'll write this all up like this. Let's get over to the blackboard. So switch. So R is my regular wage. I know my overtime wage is 1.5 R. That's overtime. And I'm going to jump back to the slide here, this back and forth. I hope it doesn't get too dizzy. A student applies for a job. The overtime wage is 1.5 the regular hourly wage. So that's the overtime wage. But we also know that the overtime wage is $15.90. So we say is $15.90. So if I want to solve for R, I divide both sides by 1.5. This is again an example of whatever you do to one side, you do to the other. and I get 10.6, or in terms of this, $10.60 per hour. All right, I'm taking a deep breath now. Okay, so there are some particular types of problems that have known equations or relationships. And I want to look at this. This is a very well-studied equation, and I'm going to look at some things that come out of it. And so we have the distance is equal to the rate or the speed you're going times time. And I'm going to look at this in its most abstract format. So, and let's switch over there. You're probably going to hear me say switch a lot. Make sure I switch. So distance equals rate times time. This can be arranged in three different ways. There are three variables. And so we could solve for each variable. And it's a good thing to kind of know what each variable can relate to, and how we can have each variable come back out of this. So the way I remember this is I always look at miles per hour, which is miles per hour times time. Well, if I multiply by hours, those will cancel. And so this is how I always remembered setting up this equation, is I have some distance times my rate, right? Because this looks just like what we did in related rates. I have a ratio of miles per hour times time. And so I always use the car as a way of putting this equation back together. I'm going to take 2 clicks back and answer Janine's question. It was linear. It was A times B, A times X plus B equals C. It just happened that the B was 0. Let me scroll up and answer Janine's question here. So Janine goes, hey, is this linear? And I can say, hey, 1.5x plus 0 equals 1590. And so there's the A times X plus B equals C. It just happens that one of them was a 0. So it is still linear for us. That was actually a really good question, worth coming back to. So I'm going to re-click here, get back on track here. Not really on track, just moving into it. So this equation, I always recreated in my head by thinking, hey, if I'm traveling in a car at 60 miles per hour and I travel for 1 hour, how far have I went? I've went 60 miles. I think you've heard me say that when the speed limit was 55, I drove 60. When the speed limit changed to 65, I still drove 60 because I could figure out how far I would need to go between each exit. So I am that old guy, but I do stay in the right lane. I don't do it in the passing lane. So I am that old guy that travels slow down the highway, but I just did it so I would know how far I go. Driving up and down the East Coast, and you're like, hey, I'm 20 miles to the exit. That's 20 minutes. Because traveling at 60 miles an hour, it's a mile a minute. But when I had to do problems like this is how I always remembered how to set this up. I'm not a memorizer, right? And so this, I'm not a memorizer, so I would always rebuild this. But what's nice about this is we can find any of the things that we need from here. So I'm going to write the 3 equations separately that come out of this. So if I start with D equals RT, but I want to know what my rate is. Well, the definition of rate's kind of neat, but I'm just gonna go here, D equals R times T, but I want to solve for R. Well, the thing that's in the way is T. So I'm going to divide this side by T, and whatever I do to one side, I do to the other, these will cancel each other out, and that gives me r, right, equals d over t. My distance divided by time is my speed. My distance divided by time is my speed. And so that's two ways we can write this one equation. Well, then the last way we can look at it is, hey, I want to solve for the speed. Or for the time. Ooh. So I'm going to solve for the time. Well, the thing in the way here is my rate. So I'm going to divide this by the rate, but whatever I do to one side, I do to the other. These will become a 1, so I'll get a t over here equals the distance divided by my speed or my rate. And so the three equations that I get from this one relationship is my distance is equal to my speed or rate times time. My speed or rate is equal to my distance divided by time. And the time I've traveled is equal to my distance divided by my rate. These relationships, any set of multiplications or any set of variables, we can solve for any one of them. And I think this goes back into Janine's question where then do we just plug things in? By having these different relationships, we can solve different problems that come out that would use different parts of it. And so having this one relationship lets us actually understand three relationships. Each variable has a different relationship, and this manipulation is neat. Now, you're lucky. You're going to be doing your exams and stuff. You're going to have your notes. I would try to take problems like this and maybe write down any formula or thing on the side. Distance problems come up a lot. This is a really good example of how a rate gets used, and I will come back to how rates are really important in linear equations. But for right now, I want to show this itself in use. So here's the problem I'm going to look at. So in Japanese baseball, I'll read it fully. One of the fastest pitchers in the history of Japanese baseball was Yoshinori Sata, whose pitches were clocked at about 147 feet per second. If the distance from the pitcher's mound to home plate is 60.5 feet, approximate the time it took Sato's pitch to reach home plate to the nearest hundredth of a second. So I'm going to leave this up here for a second, and I'm going to focus on some parts of it. So the first thing is that I'm going to underline this bit here. I'm going to notice that I have a feet per second. I have a distance per time. That's a rate. If the distance from the pitcher's mound is 60.5 feet, I have a distance. And in my head, I'm going, hey, my distance equals my rate times time, because I don't remember all three equations. So if I solve for time, time is equal to distance divided by rate. So this is the thing I remember. And I actually still have to rebuild it, and I convert it back into this. But however you want to sort your notes, it is good. Well, this is a rate. So I know R, and I know D. So I can find the time by plugging into here. So let's do that over here. So T equals D divided by R is what I'm going to use. I'll put these three up here. I'm going to just keep the same blue color. So my distance was 60.5 feet. Let's do that. So I pulled these three up top. My distance was 60.5 feet. And my rate was 147 feet per second. So my R equals 147 feet per second. So when I want to find the time, I take 60 0.5 feet divided by 147 feet per second. Notice the feet are going to cancel, and I'm dividing by something divided. That's going to put the seconds up top. So I am going to get seconds as my unit. And we'll talk more about unit checking as we do more and more word problems that start using our rates coming out. But let's run to our calculators. Remember, we're in calculator friendly land now, because there's no way I could do this long form nice and neat. And they said to the nearest thousandth of a second, so 0.412. That's the thousandths of the second. And so the time it took that baseball to reach home plate from leaving his hand was 0.412. Notice the examples we did when the word problems. We did one with an addition property, and this is one with a multiplication property. And I want to really, really emphasize, the book isn't going to emphasize it in this chapter, but when we were doing related rates, the word rate pops into this. Miles per hour is a rate, right? It's a ratio with units. And rates are going to be very, very important for dissecting linear word problems. In fact, I'm going to tell you what the future is going to talk about for us. AX plus B, just that one side of the linear equation, that A is usually a rate. A rate of change is usually what we call it. And so when you see linear problems, this multiplying thing will usually be a rate. So paying attention to where we see something per this, when we talk about our wages, it's our dollars per hour, right? It's going to be a very important part because it's going to be the part that comes out and hangs out in front of our variable. All right. So all of these properties can come together for us and give us some equations that pull together. So I want to look at some examples of linear equations that combine terms and properties. So I'm going to go through a couple book examples of these. And basically, we're working in the first 3 sections of chapter 9 in the book and chapter 12 online. And so we're looking at the first 3 sections, and I've posted homework on the first 3 sections there. Due 2 weeks because I'm giving everyone time to watch lectures. We still have that exam coming up. But I'm going to go through a couple different examples here. And then I'm going to, I've been recording examples based off of homework questions people have gave me, and I'm going to show you all that in a second here. So let me just put up this problem here. Let's scroll down here. And so we have 13z plus 5. 13z plus 5 equals minus z plus 12. And what we want to do is we want to get this into a linear form. We want the variable on one side. Now, again, it does not matter which side I take the variable to, but I don't like having negative variables. So I usually look where the biggest coefficient for the variable is, biggest positive coefficient, and I try to move over there. So I wouldn't want my variable to be on my left-hand side here. That means I have to get rid of this one. Well, if this is negative z, to get rid of it, I add a z. Oh, I said z instead of z. I've been in America too long. And whatever I do to one side, I do to the other. So over here, that leaves me with 12 on my right-hand side. And here I get 14z plus 5. Now my next step now is I have my linear form. This is linear. because I have ax plus b equals c. There's my a, there's my variable, there's my b, and there's my c. So now I want to isolate the variable. So I'm going to subtract 5 from each side. Whatever I do to one side, I do to the other. And for me, I think of this as like peeling an onion. My variable is the very center of an onion, and these are outer layers. I also tend to go in PEMDAS in opposite direction. Mostly. Sometimes I'll have to do things in parentheses first, but usually I can do things outside of them. And so I go all Shrek on it, right? The equations are like ogres, because they're like onions. They have layers. And I have to take it a layer at a time. And so if these will cancel, leaving me 14z, and this will leave me 7. Now I'm on my last layer, which is the 14. So I divide both sides by 14, and I get z is equal to 1/2. And so here we have most of the operations that we're going to see within our PEMDAS put together to help work us through. All right. Let's look at one where parentheses come into play. And there are a couple different ways you can look at this. I'm going to do this 2 ways. And I think this will be my last example for today. And then I'm going to just talk a few minutes about where we're at with some stuff. So let me scroll and see if I have enough room to do the 2 ways. Yes, I do. So I want to have 2c equals -3 times the quantity, c minus 5. All right, so there are 2 ways to look at this. And so for the first way I'm going to do this, I'm not going to care about fractions, right? I'm going to go right towards my fractions because, well, I've been doing fractions long enough. They don't bug me. Some of you might do it differently. So this first way is the I'm not scared of fractions ways. I'm going to realize that this 3 is standing in way of whatever's in here. So I'm going to divide by -3. And that's going to give me whatever you do to one side, you do to the other. And I'll just write this way out in front. Hope we can appreciate that if I divide by -3, that gives me a -2/3 c. And I'll write the c outside, not in the fraction bar. These become 1, and so that's c minus 5. All right, I am going to subtract c from both sides. So I'm going to get rid of the c here, and I'm going to subtract a c here. C and minus c will leave me with the -5 over here. Now here's where I'm going to just do a little scratch work over here. I have -2/3 c, and I'm subtracting from it 1. But 1 written in terms of thirds is -3/3. And so that gives me -5/3 c. Okay, well, I've got my variable on one side and I've got my numbers on the other, so I want to get rid of this. So I'm going to divide by that. Well, dividing is the same as multiplying by the reciprocal. If I multiply by -3/5, these will cancel. So I'm going to multiply the other side by -3/5. Handwriting day. So a negative times a negative is positive. These have canceled, leaving me c. And the 5 upstairs is going to cancel the 5 downstairs, so I get c equals 3. All right, that was me being comfortable with fractions. Let's do this in a way if we are not comfortable with fractions. So I'm going to rewrite this problem. I'll do it in bright yellow. And I'm going to do it such that I'm not going to use fractions. 2c equals negative 3 times c minus 5. So I'm going to distribute this negative 3 to each term. So it gives me negative 3c when I multiply these, plus 15 when I multiply the last term. I'm going to add 3c to both sides. And then I'm going to divide both sides by 5. And I also get c equals 3. So there are multiple ways to do these. Sometimes distributing through the parentheses will get you there quicker, as it does in this case. Other times it won't. You should be comfortable doing both on these. So Janine asks, how do we know that 3 over 3 is equal to 1? Anytime I'm subtracting 1 from a fraction, this is 1, I would have to get a common denominator. And so I could look at this as 1 over 1. And so if I get the common denominator, that would need to be 3. And so I would multiply the top and bottom by 3 to get the 3 over 3. But if we look at this is 1. What I tend to do is if I'm subtracting 1, whatever the denominator of the thing I'm going to be, I get over top of itself. So if I had, I'm going to make an ugly fraction, 583 499ths plus 1. Well, for the denominator to be the same, and I'm adding 1, it's 499, 499. I get the same thing down here up and below. It's nice with ones. It's actually good with any whole number. Let me do, I'll scroll down. I think this will be the end of my space here. If I have 4/8 plus 2, I have 4/8 plus 2 over 1. So 4/8 plus, well, this needs an eighth. So I'm going to have to multiply the top and the bottom by 8, which is 16/8. So whenever we're doing the common denominators, if these are whole numbers going into a fraction, I usually take the denominator and multiply it by this whole number and plop it over the denominator. I tend to really only see that with ones a lot coming through, but it does happen with larger numbers. All right, so that's everything I have. It gets us through the first 3 sections of this, and we're going to go back and forth. Now, one of the things I've been doing is people, and this is kind of administrative here. So I'm going to go to my web browser. Hey, there you guys are. All right, so if I come in, I'm going to open up a YouTube page here. And we'll see how, okay, so if I come into the YouTube page and I go to the playlists I've created, there's this playlist of 092, and all our lectures are going to end up in here. But also, if someone is asking me a problem in the book and I make a video for it, I am putting the problem up here. So someone had asked me problem 4, or section 4, problem 39. So I recorded a video to it. I'm also going to be recording short videos now of examples outside of the lecture format. So any of these examples that I want to emphasize or do, I will add to this playlist. So the link to that playlist I put on Blackboard. So let me come back over here, and I go to my course content in Blackboard, and I have, I want to say in here, oh, that does not, okay, let me, I thought I plopped it up. I think I put it in the email here. See, this is a good thing to check. So I will copy that link. And to Matt 092 playlist. And I will be, and so you can go up there and you can see the questions other people may have asked in homework. You can see some worked out examples of those. If you have a question in homework and email me, and I don't cover it in class, I will tend to put the lecture up there. Get back to you guys here. And so that in itself is in Blackboard now. Okay, I'm going to do this because I'm talking. That's everything I have for today. We've got a big chunk there. I have the homework up on it. I really want you guys to get your exams in and be okay with that. Sorry about our guest appearances today. There's probably not going to be a way I'm going to be able to deal with it, but ahead of time, but when I do see it, I might take a minute to stop through. Sorry, it also flustered me. I should be better than that. I've worked in internet security long enough before coming here that I should be used to things like this. All right. If you have any questions, holler. Keep sending the emails. I'll keep putting examples up there. Work through in Pearson. If you have any problems with anything, just let me know. It goes back to Stacy's question, but anyone question on doing an online exam, it's different. That's why I'm letting multiple attempts. That's why I have practice versions of it up there. I know Pearson has had some issues. We all have scheduling issues. Just talk to me. Email me. Tell me what's up. And if we're communicating, I can adapt. All right. Be safe. Be well. And if you need anything, I'm here.